Well, hello everyone. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra, and welcome to this webinar highlighting QuEra software partners. Um, today, we have some distinguished presenters. Kenny from qBraid. Hey, Kenny.
Hello.
James from Strangeworks. How are you doing, James?
Hello, I'm doing good, thank you. How are you?
And Peter from AWS Braket. Hi, Peter.
Hi, everyone.
Um, and as you can see, Kenny is Vice President of R&D at qBraid. Peter is Applied Scientist at Braket, and James is Quantum Software Engineer at Strangeworks. And the way we are thinking about structuring this is that I'll provide a brief introduction about QuEra, but then we'll turn the focus to our three software partners that are here today. Peter will present AWS, Kenny will present qBraid, and James will present Strangeworks. And what I've asked each of our presenters is to talk about their platforms, why are people using it, what are the advantages of doing so, and then obviously to demonstrate how does one create and submit a job to Aquila's computer. So briefly about QuEra. QuEra is based in Boston, close to Harvard and MIT, and our closeness is both geographic as well as intellectual. We have very strong collaboration with Harvard and MIT, and we have been experts at commercializing inventions that were made at Harvard and MIT, and of course, under license, together with additional developments done at QuEra, and we brought them to market very quickly. We build quantum computers using neutral atoms. There are many ways to build quantum computers, and we believe that neutral atoms is really the best way to do so. The reason we think that is that neutral atoms operate at room temperature. They provide a high degree of scalability. You can put very many qubits on a single machine. Qubits are dynamic. You could move them around and thus create better algorithms, more efficient algorithms, and new ways to do error correction. And also, qubits are natural, so they're naturally perfect. They're naturally identical. We have been deployed on AWS Braket live since November 22. Peter, again, thank you for your partnership. So people from all over the world can use QuEra today. All you need is a credit card or an AWS Braket account. And also, you could use them through our partners. So if you have a qBraid account or a Strangeworks account, you could use it this way as well. And we believe that we are both the scientific as well as the commercial leader in neutral atoms. And many, many people use QuEra today for a wide variety of simulation, optimization, and machine learning. In the last few months, we've announced a couple of major milestones in our journey. The first one was that we signed a deal to deliver an on-premises quantum computer, a gate-based quantum computer to AIST, the National Institute of Standards in Japan. Another big milestone for us is that we were selected to deliver a machine to UKRI, to the UK National Quantum Program. And thirdly, not too long ago, we announced a major investment from Google at QuEra, and more details will be forthcoming in the next couple of months. We're here to talk about our initial machine, the 256 qubit Aquila. As I mentioned, was launched in 2022 on Amazon Braket. 2 years later, it remains the only publicly accessible neutral atom machine. And I think as measured by the number of qubits, it's probably the largest publicly accessible machine in the world. Aquila is available for about 130 hours a week. So really no excuse of not using it, because you can almost always get a job submitted and executed very quickly. And as I mentioned, key applications in many areas, and that the use of Aquila has resulted in many interesting scientific and commercial papers, from BMW, for instance, from JP Morgan, from others. Of course, Aquila was launched in 2022, and we continue to work on next generation machines. Here's a brief video of one of the upcoming machines that we are developing in our labs. And again, more details to come in the future. And there are a couple of different ways to work with QuEra. One way is to use QuEra over the cloud. and we'll see how we do that with some of our software partners. Another way is what we call co-design or joint development, where you could collaborate with us. There's also a very experienced team at AWS to do that, and really co-design algorithms that make the best use of the machine. And of course, if your budget allows it, we would be more than happy to sell your machine. And what you see on the right side, on the left side of the screen, is how this looks. This is a container that will deliver one of our machines to one of its destinations. And of course, it's not only a quantum computer, but you also get the installation, the support, the on-site people to make sure that you can make the most out of your investment. A couple of months ago, we launched the QuEra Quantum Alliance, and this is one reason that we're here. The QuEra Quantum Alliance has market leaders that all come together to maximize the potential of neutral atom computers. As you can see, both Strangeworks and qBraid are there. I guess AWS is, I would call, a founding member, even though the logo is not officially here. And we would really love software partners or integration partners to join the Quantum Alliance. Just give us a call and we'll see how we can get you involved. So with that, hopefully I wasn't too quickly. Peter, maybe you could spend some time describing AWS Braket and how to use it to access Aquila.
So I will go through a couple slides and I will jump into a demo. This will be about Aquila only, but I will start with a brief summary of what Amazon Braket is. And briefly, Amazon Braket is just another AWS service. This is one of the philosophies that we followed when we launched Amazon Braket about 5 years ago. Specifically from the quantum computing side, Amazon Braket is a complete system which allows you to build, test, run your quantum workloads and analyze the results. You may exit or enter at any stage, at any level. So the idea is that there are multiple endpoints, multiple levels of access to the different devices, and different levels of abstraction. So depending on how complicated your workload is or how much control you want to exert over the type of programs that are running, you can choose to do so. So let me jump quickly to the current family of QPUs that are available on Amazon Braket. First and foremost, the Aquila device, which we will hear most about today. And that accepts a computational paradigm called analog Hamiltonian simulation, or in short, an analog program. And there are 3 other families from IonQ, Rigetti, and IQM. Each of these devices are accepting quantum circuits as the computational paradigm. As the philosophy of Amazon Braket, we are following the general idea that we don't know which of these devices will bring eventual value to humanity as they scale up, and so we are basically technology agnostic. We are open to new type of paradigms and hope to make this portfolio even bigger over time. This is a brief maybe summary or bird's eye view of our philosophy of the software stack. So people can enter at this stack at different levels. They could choose to directly access the service APIs, which would be the penultimate level here. But they can also choose to access at the SDK level, which would be the second level, titled circuits and low-level control. Or if they choose to, they can use Penlane, Qiskit, Blockade, and many other tools, including Strangeworks and including qBraid, to craft the programs and then submit those programs that then propagates through the stack and eventually bubbles up the results to the right level of access. I will use the Python SDK today for demo. So this is the slide about that. Feel free to grab the QR code. This is an open source tool, easy to install. It also comes pre-installed in our managed containers, as well as the notebooks that they're coming and available on the Amazon Braket service. It comes with a bunch of simulators that can simulate state vectors, density matrices, as well as AHS, analog Hamiltonian simulation programs. A more experimental branch of our SDK strategy is Braket plus Julia. So that means we are branching out. We are offering the same capabilities, exactly the same functionality to Julia users. So that is implemented by Braket.jl, which is, again, an open source library. It is available, waiting for contributions. It integrates well with Blockade and other Julia modules. An even more experimental library is Braket HSJL, which is an efficient Rydberg simulator. This works up to 200 atoms, and it uses an MPS approximation of the trotterized evolution of the Rydberg atom array. And all of these are available open source. Feel free to grab them, give them a test ride. And as I mentioned already, Braket also comes with the managed environment. Once you have a Braket account, you log onto the console and you can fire up a notebook. You don't have to deal with the dependencies on your local machine. As usual, it comes with a small amount of cost when you are using AWS resources to maintain these notebooks, but it gives you a good start when you don't want to maintain the dependency tree on your local system. And with that, I will jump into the demo. I will follow a simplified version of an example notebook, which you can find at this link. This is one of the many example notebooks that are available. And I will attempt to switch my screen to that particular window. And this is the notebook. You can find it on GitHub. This notebook starts simple. Discusses what Aquila is and how to submit the program. I will run through that live. So I will go through the cells. I will execute them live, not cheating. I will restart the kernel. You can see that all of that is happening. So you can initialize access by importing Braket AWS and Braket devices, and then this can define the Aquila device. If you do that, this will execute, and then this will show you the capabilities of that device. This is fairly raw or low level, but that's exactly the purpose. We want to give full control over what the device is. All of that information is, of course, vended to us through QuEra, but we are making it available such that if there's any question about what these mean, then we can find the meaning of these fields separately. So later, when we go to this cell, we can separately look at some parts. Let's say the lattice constants. It tells us how big the lattice can be, how much the spacing should be, and then if we want to know what these each mean, we can print them out by referring to the docstrings portion of the schema that's part of the SDK. And we keep these updated whenever we know a bit more, or whenever QuEra tells us to update these things. We update these numbers, so they're always accurate and tells you what the device can do and what these numbers mean. Then let's jump into a specific example. We will attempt to create a lattice such as this. As you can see, this is a bunch of triangles. The atoms are separated such that they don't interact except the neighboring 2 or neighboring 3 atoms. And what we will do is we will start by initializing the atom arrangement object. Initially, it's empty, as you can see here. And then what we do is we separate it into blocks. The goal is to have a 5x5 set of blocks, and then we will add the top atom here, the bottom left atom here, and the bottom right atom here. All of that is, of course, codified. So if I execute this cell, that I print the array, then it shows that indeed that's what I created. The next thing that we need to create is the driving field. That's what we do here. There's a bit of explanation, part of the notebook, so we don't get lost in the notation. But really, what we want to know is what is possible numerically. All of the values are stored as decimals. It tells you how far you can go with the different fields, how strong they can be. And we found that decimals work pretty well. They serialize well. And so that's why it's printed like that. Again, if we want to know the meaning, we can list them out by referring to the docstrings portion of these objects. Again, what we want to create is a trapezoid pulse. So we will keep the amplitude to the simplest one, which is a trapezoid up ramp, a constant plateau, and a down ramp. And we'll keep the detuning the phase constant 0. So that's going to be easy. What we use is a time series object to construct the amplitude. And we have a trapezoid signal constructor here, which takes a couple of parameters here, after which we can feed this into the constructor of the driving field. All 3 of the amplitude, detuning, and phase are then constructed. And if all goes well, this shows exactly what we wanted to do. Finally, the local detuning is an experimental feature which is available on Amazon Braket. You need to request it, but otherwise, once it's enabled on your account, you can use it. To learn more, you can again list the capabilities from the original document that comes with the device, and then you can list the meaning of each of these. To define the actual field, I think I need to open this cell up. Not sure if maybe we're not even defining local detuning in this. I think that's exactly right. So we could define the local detuning field. We can add it to the Hamiltonian, but in this example, we're not doing that. If we want to put all of this together, then we define the register and the Hamiltonian being equal to the driving field, and then we create this program, analog Hamiltonian simulation. Now this packages everything together. This program can also be serialized, can save to the disk, can send it in an email to a friend, and they can deserialize it and start from this checkpoint. The last piece, which is again kind of a low-level exposure to the device, it shows us that we need to discretize this program. That means some of the floats, which we indeed defined in the register, need to be converted to decimals with the right precision. And the reason we decided to do that is because once you do this step, the discretized program is slightly different from what you originally defined, but no matter what, this actually allows you to investigate, and if you're happy with this program, you can proceed. So we discretize, that program now has decimals, and we can submit. So this is exactly what's going to happen. I define the number of shots, and then I will submit. I will submit to the device. The device is currently online, which means it accepts tasks, but it is not available. Which means it's not processing them. So if we get the task object back, the task object has a bunch of metadata, which I can query. And what I get is it tells me that it's queued. I can check it on the console, so that's another tab. And if I refresh this page, I should be able to see the task that I just created. So the queued task is sitting here. The device is currently not processing, which means it will still here for until, I think, tomorrow. So we're not going to wait until then. I will grab a task I created originally for this demo, which has a different ID. If you squint, you can see. What this tells us is you can grab a task that you worked on previously using the same notebook, which we're going to do here, and then we can see what happens with that task. So that task is completed. That's one of the tasks down below. I think it's this one. And with that, we can proceed. I can take the task. I can get the results. The way it looks like is that it contains the raw results. So we're not changing anything. We're exposing everything to the customer. You can choose to work with these results, or you can choose to use some of our post-processing methods, such as get counts here, to learn a bit more about what it means. So now you see the ones and zeros turned into G's, R's, and indeed sometimes there is an E hiding in this, and I will attempt to find one. But sometimes an atom is missing, in which case we mark that site with an E. And that allows you to post-select. You can choose to not use that result in your results, in your analysis. We can proceed using the counts data. We will go through, we'll iterate through the counts. We will use the geometry that we defined previously to post-process our results, running through the different K and M indices in the blocks. And then we collect the number of times a Rydberg atom was present in these triangles. So let's do that. And I hope so that worked, and then we can plot it. So what we see here as a final result is that analyzed for each triangle, the atoms in that triangle is roughly equally excited in the Rydberg state. So that's the first plot. And then the number of atoms in each triangle is typically 1. And that's what we wanted to see. That means they're close enough that they're blocking each other. At most, one of them is excited. So that is demo. And I think we can move on. Thank you very much.
Thank you very much, Peter. And I understand that there are many other example notebooks, also both directly from QuEra and also from Braket, to showcase simulation, optimization, machine learning. We had some really nice machine learning results with quantum reservoir computing.
Indeed, that's absolutely true. Thank you for highlighting. So we have a bunch of other sources where you can take a look and follow if you want to learn more.
Wonderful. Okay, well, thank you, Peter. Kay, would you like to go next?
Absolutely. Let me go ahead and share my screen. All right. Well, yeah, first of all, thank you to Yuval and QuEra for having qBraid here today. We're happy to present a little bit on our platform and some of the software and how it integrates well with QuEra, as well as kind of demonstrate how you can access QuEra through our platform. And thanks again to Peter, who just gave a really nice demonstration of AWS Braket. We're going to be using Braket behind the scenes, so everything that he's just discussed will be getting used behind the scenes by our platform in one way or another. So I'll do some slides to start off with, and then I'll go ahead and do a little live demo. Yeah, that'll be it. So for QBraid, we're your one-stop quantum platform. We're a Chicago-based quantum computing startup. We've been around for a little bit at this point. Today, I'm going to mainly focus on the software aspects of what we provide. We do a lot of research, which we actually do in collaboration with QuEra on applications in quantum for biology, among other things. But today, I'm just going to focus on the things that you see here. So basically, what we try to do here at QBraid is give people a seamless experience for both getting onboarded into quantum computing, getting into quantum computing, even if they're a developer, if they want to start submitting jobs, if they're kind of an intermediate level. And then we also want to give quantum hardware companies the opportunity to more easily deploy some of the services that they might want to expose to their customers. So we do that through a number of different tools, the ones that are listed here. The first one, which I'll talk about, is Qbook, which is our learning platform, more tailored toward people who are just getting started out. And then we have QBraid Lab, which I'll be doing mainly the live demo of, which is more of a exploratory sandbox where basically all access to quantum computers, as well as all of the quantum software in the ecosystem, is basically pre-configured in a cloud-hosted instance that you can access from anywhere. And then I'll talk about the QBraid SDK, which is our open source Python SDK, which kind of helps you work both locally as well as allow you to work in a quantum SDK agnostic way. And then I'll talk a little bit about QBraid Runtime, which is more of a service that's tailored toward quantum hardware companies that want to deploy various services. So first of all, we've got Qbook. This has been a very successful quantum learning platform at this point. In fact, if you go to, I believe, qbook.qera.com, you'll actually find QuEra's version, white labeled version of this product that we've developed. And so basically what it is it's a interactive learning experience where you can write both code, text, video, animations, widgets that you can modify with little sliders in a really, really straightforward way, that you can connect to a compute backend that has the environment set up as you want. So if you're somebody like QuEra and you want to make a blockade Python or blockade Julia available in the backend, doing that is a relatively straightforward experience. So you can put together this nice, seamless experience for your students. They just log into a single spot, they watch some videos, they read some text, they execute some code, and it all just works very, very straightforwardly. At the end of it, there's a straightforward workflow where you can generate certificates. People like to post these things on LinkedIn, various social media platforms, and whatnot. So that's a very, very high level overview of Qbook. Again, I'll show this a little bit as time allows. But now I'll move on to QBraid Lab. So basically what QBraid Lab is we say it's the ultimate quantum development environment. Obviously, we're all presenting some version of a quantum development environment here. So you're free to choose, whatever works best for you. Basically what QBraid Lab is it is a hosted Jupyter Lab environment with things pre-configured in the backend that make it straightforward to access quantum computers without having to manage a bunch of different accounts. So, while you can, go on to Amazon, you can make yourself an account there, and then you can therefore access quantum computers via AWS. You might also be interested in accessing quantum computers through IBM, through services that are only accessible via Microsoft Azure, etc. So via QBraid, we basically make all of that available through our backend in a very straightforward way where you make a single QBraid account and you can log in and access all of these things in one spot without having to manage multiple accounts. So that's one big feature of QBraid Lab. As I'll show in a little bit, we also basically package up all the software in a really nice way so you don't have to worry about making sure that works out of the box. It just all works when you sign in. So that's QBraid Lab. The QBraid SDK is actually an open source Python SDK that you can both use right off the shelf, as well as contribute to if you want to, since it is an open source Python project. The primary goal of the QBraid SDK has been to allow people to code in whatever framework they want, be that Qiskit, Cirq, PyQuil, now Quantum Intermediate Representation, or QIR is one, and a bunch of others. Basically, you can code in any of these, and then you can always transpile to a different framework, as is depicted in this little graphic right here, and then you can submit to backends that are only supported via that other framework. So this makes it really nice to kind of avoid vendor lock-in when it comes to various software libraries. Makes it relatively easy and streamlined for users to start adopting quantum computing. And then also, more recently, we've been making it more and more possible to actually use the qBraid SDK in your local development environment to submit jobs to quantum computers just using a single qBraid API key. And so I'll show that in a little bit as well. And the last thing is qBraid Runtime. Again, this is more of a product that is oriented toward entities that want to basically provide access to some kind of hardware or software more at scale. And so basically what this is an orchestration framework where we make it really, really easy for those types of entities to come into qBraid and tell us, hey, like, we've got this piece of software that we want to run on very, very scalable compute. We want to not worry about the credits management, the user management, how all of that works. We just have the software, or we have this quantum computer, or we have this classical computer. We want to make it available to people. We have a really, really nice framework for doing that that connects up super nicely with our lab instances and with access through the qBraid SDK, like I'll show in a little bit. And actually, as of recently, with QuEra, we've been working on making access to compiler simulator infrastructure for their upcoming Gemini devices available via qBraid, and is actually currently available to a select number of customers. So now is the time for the live demo. So I'll go ahead and stop this screen share. Come on over here. Well, I guess I could have just stayed on that screen. Okay. Cool. So first of all, if you want to follow along, you're more than welcome to at this point. qBraid is easy enough where, you can get set up basically in the amount of time that I'm going to be talking right now. So what you can do if you want to is you can come over to account.qbraid.com. You can either sign in with Google Sign-In, or you can just sign in with a username and password that you come up with. Once you log in, you'll be greeted with a screen that looks something like this, although probably a little bit different because you likely didn't sign up with any kind of subscription in place. That's totally fine. You actually don't need a subscription to kind of get a taste of qBraid. If you do sign in, I'm just going to let you know right now that you can click this little manage button. You can come on over to this access key right here, and you can enter HNew6626, and then you can hit submit, and that'll just give you some credits that you can start playing around with. You don't need to pay anything per month. It'll just give you some credits where you can start playing around with quantum computers and the other resources that we provide access to. So to give a little bit of an overview of the platform, we offer a bunch of different plans, which you can pay for on a monthly basis, or you can stay on the free plan. Basically, buying these different plans gives you access to different levels of compute instances that run in the back end when I show a Jupyter Lab instance in a moment. But at the end of the day, if all you're really interested in doing is running quantum jobs, well, then you can just stay on the free instance. You can buy credits that you can use to submit quantum jobs, and then you can just go that way as long as you want. And then, so obviously, your credits will be shown here, your plan will be shown here. And then right here, obviously, this is blocked out, so you can't see it, as your qBraid API key. So this is basically your gateway to accessing all of the qBraid ecosystem and all the things that we give you access to, both via the hosted instances that we show and via local instances. So you can copy this and get started locally if you want to start playing around with the qBraid SDK. And one really nice thing that I want to highlight right now for the people who are kind of evaluating why you might use qBraid is the following. So while you can join qBraid as an individual, it's actually really, really nice if you're an organization who's starting to try out quantum computing. So what you can do is you can talk to us about getting set up with organizational access, which is relatively straightforward. You can make your own organization, and then you can add people to it. In this case, I've got a fake organization that I've got called Kenny's Club. It consists of me and me again. Obviously, it looks like my other alter ego didn't actually accept this other invitation, so that's okay. This is just a demo. But basically what you can do is you can add all the people in your organization to this org right here, and then you can buy credits for the organization. And then basically what you can do is you can manage people's access to those credits. So one problem that I've observed, at least from managing quantum computer access at universities sometimes and at other organizations, is that a lot of times like making sure that the IAM permissions and other types of permissions that you have to set up via a cloud setup, like maybe Amazon or IBM or Microsoft, can be a little bit complicated for some organizations, and they don't really want to deal with that. So what ends up happening is that one account on one of these cloud services ends up having a big old bucket of credits that everybody has access to. And obviously the problem is when everybody has access to the same bucket of credits, somebody can accidentally scoop up too many of them, and then everyone cries out that they've been, stolen from or something. So what we do here at QBraid is make it relatively easy for you to avoid these types of instances and make it easy for people to use credits without having access to the whole bucket of credits. So what you can do is you can make an org, you can buy credits for the org, and then you can come in here after you've added people and you can select them and you can say, how many credits I want to add to this one person right here. For example, I could add 1,000 credits to Kenny at QBraid. They would go through. In this case, it's not going to work because I don't have enough credits in the org. I think maybe I have like 50 or so. And so there you go. It'll just go straight through. And you can do that in mass for many, many people. So, you don't have to click every single one. You could just select all of them or something and then distribute like 1,000 credits to just start testing things out. You can also manage people's ability to dole out credits. So, there will be account owners, there will be super admins, managers, and users. Every single person here has a different level of responsibility and access to the organization. But at the end of the day, it makes it really, really easy for you to manage access to quantum computers and hardware. So that was one thing I wanted to highlight. We have a bunch of other things on here, but I won't take up too much time. What I'll focus on now is our lab instance. So once you log in to QBraid, you can come in here. If you're on a free account, you can just use the free instance, which will give you 2 virtual CPUs and 4 gigabytes of RAM. You can go ahead and click launch. And what this will do in the background is spawn a Jupyter Lab instance, which will probably look very, very familiar to what Peter was just showing you. But on top of the kind of vanilla Jupyter Lab experience, we've kind of added a bunch of extra enhancements that make it easier to interact with quantum computers in a really, really nice way. And so what you'll see here on the right-hand side are some semi-unique extensions that we've developed in addition to the normal Jupyter Lab environment. So what we've built are Devices Manager, Jobs Manager, and an Environment Manager. So I'll go through these one by one, highlighting where QuEra and Aquila access comes into play. Here in the Devices Manager, after you've logged in and set up a lab instance, you'll see all the different providers that you have access to through QBraid. So if you go through here, you'll see more and more on the other page, and this list just keeps on growing longer and longer. If you're interested, you can go on and you can obviously, click on one of these and get more information about it. For example, here's QuEra's Aquila device. It'll tell you something about the paradigm of the device. In this case, it's an analog Hamiltonian simulator. It tells you the architecture, neutral atoms, how many qubits, clearly the most of any of the quantum computers in this list right here. And then importantly, for right now, it'll show you the next time that Aquila is actually going to be available. So right now it is not available to send jobs to and have execute immediately. So whatever we submit right now through QBraid will just sit in the queue and then execute after this time elapses. And then it also shows you what kind of access we're using on our backend that we actually build out to submit jobs to Aquila. And in this case, what we're using is exactly what Peter was just commenting on or talking about, which is the Amazon Braket service. Then we also list, the Amazon resource number, which you can always copy and paste into the notebooks that you want to execute jobs to. And then also, a lot of people care about how much these things are going to cost. So you can obviously see the pricing for any of these devices. In this case, It's going to be 30 credits per task and 1 credit per shot. And then likewise, you can see the same things for any of the other devices. For example, if you wanted to submit to IonQ, you click on that, you would see all the same information and so on.
Kenny, if you could move to a demo soon, that would be fantastic.
Okay, fine. All right, we'll speed this up quickly. So yeah, moving on a little bit, we've got the jobs manager, where we show all the different jobs that you've submitted via QBraid. What you can do is you can go in here, you can click, and you can see basically a lot of information that's related to your job. And what I'm going to show right now is actually a demo of how you submit this via QBraid. So let me go in here to the demos folder that I made up for this talk. The first one's going to look very, very similar to what Peter had just shown. So we won't go through it as much line by line, but I'll just simply show you that it works and how it interacts with some of the extensions that we've built out. So the one thing that I didn't talk about too much is this environment manager. If you don't want to fuss around too much with managing dependencies for your Python environments, you can always come over here. You can find the Python environment that you want. In this case, we're going to be using Amazon Braket for submitting jobs. And you can come over here, you can click install. I already got it installed, so I'm not going to do that right now. So I've got Amazon Braket v1.86, and these are all guaranteed to work out of the box on QBraid, so you don't have to worry about any dependency issues. So in this notebook, I'm just going to make sure that I've selected that instance, that environment. Let's see, Braket v1.86. And once we've done that, we should just be able to execute code here without having to enter any AWS API keys of any sort or do any extra setup. So we're just going to go through, execute all of these lines. They should just take a few seconds. As you can see, this is exactly the same demo that Peter was showing. In fact, we've pulled this exactly from AWS Braket. So I'm just going to go through, execute all these lines. And then what I want you to keep an eye on is this jobs manager right here. So once I actually submit the job, which will happen right at this line, what we can do is refresh this, and we'll see that the job that we just submitted via this notebook shows up in this sidebar. So we can see what we submitted this job to, in this case, Aquila, how many shots we took, how many credits we're spending, and so on and so forth. So that's one method of accessing Aquila through QBraid. So very, very straightforward. You just load up a notebook, load up the environment, start submitting. You don't need to set up any other API keys. Another way that we have recently been developing is the ability to do the exact same thing through Blockade, Python that is. So you can activate the Blockade Python environment. You can come in here, you can start importing Blockade Python, define your analog Hamiltonian simulator program, and then right here is where we actually run the code on Braket Aquila. So if we execute this and come over to the sidebar manager, after it finishes executing, we should see that it pops up over here. And things might be moving a little bit more slowly on this side just because Aquila is currently not accepting and running programs. And then in the very near future, we're actually going to be doing a direct integration with Aquila, where you can also submit directly via QBraid. We'll be exposing some slightly extra functionality on top of what you might be getting from Braket. Third, and I promise I'll be done in just like another minute, is that you can actually submit via the QBraid SDK. So you can come over here. Here's another notebook where I'm going to use the QBraid SDK to submit my job. I can come through. I think I've already run this potentially. You can construct your program just like you would have done previously. And then rather than submitting via the Braket methods that I've shown just previously, you can use what's called our QBraid provider. So as long as you set the provider to QBraid provider, then you can use the QuEra Aquila device via QBraid provider. In this case, it'll show it's unavailable. But then you can go on through, submit the program in exactly the same way you would have seen before. So that's all that's happening here. We defined our device, and then we're doing device.run this program. And then last but not least, I just wanted to highlight this integration that we've done with QuEra very recently. where we actually have the ability now to simulate their gate-based device. This is not publicly available, but it is something that we just wanted to highlight very quickly. So you can go ahead via the qBraid provider. You can set the QuEra chasm simulator, and you can submit circuits and get results back. In this case, it's just going to run a basic GHD circuit using 5 qubits. I won't spend any more time. The last thing I wanted to say was that you can take any of these notebooks that use the qBraid SDK, and locally, if you want to use them, you just take the qBraid provider, you put in API key equals your API key, whatever it is, and you can run all of this locally as well. So you can run both via our cloud-hosted instances as well as locally. Thank you very much.
Thank you very much, Kenny. And James would love to see the Strangeworks version of this. And one question that came up from the audience, and maybe you could address it, James, when you present, and then I'll also ask Peter and Kenny to address it, is since the underlying computer is the same, what is the difference? Why would one opt to use qBraid versus the core Braket SDK versus Strangeworks or anything like that? So, James, the floor is yours.
Brilliant. Okay, so I don't have any slides today, so I'm just going to jump into the Strangeworks portal homepage, but I will answer those questions, and I'll talk a bit about the kind of philosophy of Strangeworks and why Strangeworks. So our philosophy is to provide agnostic, seamless access to quantum computers, managed applications, and exotic compute hardware. So we provide access to Amazon Braket, but we also provide access to Microsoft Azure. We provide access to IBM. We have lots of different optimization providers as well. And we have those available through our managed application service, the optimization service. We also have kind of add-on services like QA service, VQE, integrations with different SDKs, like some part, like one of the other QuEra Quantum Alliance partners, Wolfram, as well as MATLAB MathWorks. So yeah, I think what we focused on really is kind of the quality of life for enterprise users and kind of organizations to be able to manage all of that in one place. So AWS is a brilliant tool. Nothing is AWS. It's a lot of kind of like bare bones controls and stuff in there, which for the average user, they may not want to have access to that or kind of manage a lot of that kind of workspace stuff within an AWS workspace and then be able to kind of reuse credits, for example, across accounts. So we make that really easy. We have a kind of catalog here, a bunch of compute providers, AWS, D-Wave, lots and lots of different backends, ranging across quantum-inspired, classical optimization, GPUs, and then managed applications. So that's one aspect of it. I'll speak a bit about kind of workspace management as well. So see, I've got this workspace set up. So we provide lots and lots of granularity when it comes down to billing. So you could top up with, say, $1,000 and use that across all of the different solvers kind of agnostically. Or you can maybe say, okay, I want to assign just $100 to D-Wave or just $100 to QuEra, for example, and we'll kind of split that out so that you are like able to control which resources or which kind of providers you use. We also have workspace kind of membership control. So we can, for example, see Stuart here. We can make him an admin. We can make him a member. We can set spending limits and so on. So this makes it a lot easier to kind of manage quantum jobs and kind of quantum inspired jobs. So it's a lot more focused on the kind of that use case. It's all based around an API key. So with Strangeworks, a single API key gives you access through each of our different SDKs to all of the different services as long as you have those activated. So I'd like to go over to resources. So today I've set up this workspace. We've got Amazon Braket. I'm going to show you a really, really quick example that we've seen already a couple of times today. And then I'm just show you how it's done on Strangeworks. Then I'm going to talk you through the optimization service. And then I want to talk you to you about workflows, which is something that we've been working on at Strangeworks. And this is a tool to promote experimentation and to kind of just speed up the operational efficiency of the scientific workflow. So running quantum circuits just a lot more easier and intuitive for users. So I'll jump into that. We go over to the documentation. So you can find this at docs.strangeworks.com. We provide a range of different libraries. So this is the Strangeworks vanilla SDK. You can do things like tagging and retrieving jobs, for example, which is a feature I find really useful. So, when you're working in a workspace and you've got lots of different types of jobs, maybe on different backends, being able to kind of tag those and kind of give them different, retrieve those based on the types of projects that you're working on is really helpful. So this is kind of the core SDK. And then depending on what kind of hardware or backends you want to use, we've got the optimization service, we've got the Azure Quantum, Braket, Qiskit, we have a direct Rigetti, the integration, and we have MATLAB and Mathematica SDKs also. On the optimization providers, I think we have the largest catalog of optimization providers, ranging from kind of D-Wave quantum annealing, quantum inspired digital annealing, and classical solvers like Gurobi. Then on the quantum backends front, we've got IBM, IonQ, IQM, Continuum, QuEra, Rigetti. So that's, like I say, across Azure, AWS, and the direct integrations with IBM and Rigetti. So QuEra, of course, is available through Braket on Aquila. So we have two different processes available. So we have the Braket.Aquila. So this is an optimization backend that we've actually set up to integrate with our optimization service, as well as the kind of direct AWS integration. So I'll talk about that first. We're going to install Strangeworks Braket. So this is our kind of Braket add-on service. It functions virtually identical to the AWS service, except that we're using this Strangeworks device. So it should be pretty familiar. And yeah, I'll jump into a notebook. I'll share the link to this afterwards. You can run this in Google Colab. Seems like my runtime is disconnected, so I'll just quickly refresh that. So yeah, first of all, we're going to install Strangeworks Braket. I won't spend too long talking about this because I think this is probably the third time we've seen this example, but just to show you how it's done on Strangeworks, we've set up our API key in our environment. Simple as Strangeworks.authenticate API key. Yeah, always try and use secrets if you can. If you're running locally, you can just set this up like this. Bunch of imports. Like I've said, we've seen this already, but this time we're importing Strangeworks Braket and the Strangeworks device. And I think this is installed, yeah. So we'll just run through these. See if the device is online. So we've got an atom register, the driving parameters, and then executing the circuit. Great, so if we go back to the home page now, we can see that this will have submitted. So you can see this is running on Amazon Braket. And one thing I like about this view is that in this jobs view, you can actually see the Aquila register, as well as the driving frequency. So I think this is really nice when you're viewing the jobs to be able to see that. We'll see if this finishes. I won't wait for this to run. I've got a job that I ran earlier just for the sake of the demo, and we get the results back. And there we go. So yeah, that's just a really quick example of how to access QuEra through Strangeworks. I'm going to jump ahead now to the optimization service. So we have the optimization service, and this allows you to submit a number of different problems ranging from QBOs, DQMs, linear programming problems, mathematical, MPS files, and a number of different kind of formats. And one of those formats is the unit disk graph problem. So you may have seen this problem before. I'm just going to show you a really quick example of the unit disk graph. And then I'm going to show you how we can do the same problem again with Strangeworks workflows and make it a bit more interesting. So once again, we're going to set up our problem, define the model. So here we have a graph, and we're doing the unit disk graph problem. So we want to see how many of these nodes we can kind of activate with them without having any connections between them. So no edges. So we're going to run the job. Wait for it to return us the job slug. Great, and now what you'll see is that with the optimization service, so this is a managed application that actually provides an abstraction layer between all of the different optimization backends that we have available, and kind of ties them all together. So you have all of the information. You can see the QBO that was actually submitted. You can see the optimization job information, and you can see the graph that was submitted. And then we've actually got this sub job created. So in the backend, you can actually see the job that was running on Aquila and kind of access all of that information. So no information is lost. We kind of keep all of the information that was run. And then once again, I'm going to run an example of one we did previously. And here you can see this is the solution. We've got these 3 nodes here, and there's no connections between them. Obviously, this is a very toy problem. It doesn't really tell you much. There's not really much applications. You may have seen the Aquila demo with the telephone mast poles. So we wanted to kind of put a bit of a twist on that. I'm speaking to you today from Strangeworks. So Strangeworks is actually based in Austin, Texas. So I just wanted to show you a fun example of how to use Strangeworks workflows. So this is a new tool that we've been developing, and it uses large language models to kind of help with the scientific discovery process, as well as helping users to submit jobs using agents. So I've got this conversation. Don't think we've got time to run it live today, so I'll just show you the pre-run conversation. But I said, hey, can you help me? I'm trying to find optimal places to build barbecue joints in Austin. How would I solve this optimization problem using QuEra's Aquila device? And the assistant has a Strangeworks docs loaded in as context, so it knows, okay, we need to define the nodes, we need to define the constraints because it's a unit disk graph problem, and then we need to prepare the data, so give us a JSON file, and then submit the job to Strangeworks, and then analyze the results. So I said, okay, great. Here's a map of Austin. It's got the map. I give it the coordinates, and I ask it to visualize with a unit disk radius of 1000. Here's the map. So kind of a messy collection of nodes. There's lots and lots of different edges between all of these. It seems like kind of intuitively the unit disk radius is a little bit too large in this case. So what I like about this is we can really easily tweak things. So we can say, okay, well, how can we adjust this to 640? And then we have this, and this seems a lot nicer. Kind of visually, it seems like a lot more intuitive. You can imagine if you put a barbecue joint here and a barbecue joint here, you're going to lose profits because the customers are going to probably not know which one to go to, and you're going to have the operating cost of 2 restaurants. So you want to have them spread out right across the city. So we can say, cool, let's submit this. So it submits the job, it creates it for us, and then we ask it to fetch the results, and here they are. And we can see the job that was actually submit on the platform. So this is the job. We've got the sub job as well. We can see the solution. And like I say, one of the really nice features I like is that we can tag jobs as well. So the demos that we've done today, these are the jobs, and I've tagged them all as QuEra demo. And you can do some quite nice kind of querying and stuff as we're running experiments and like different types of jobs. I found that really useful. So yeah, there you go. That's a quick run through of Strangeworks.
Thank you very much, James. So we have maybe 3 or 4 minutes before we wrap up. And I wanted to ask Peter, we've seen all these different environments, anything from the very, very high level AI-powered solver to some of the very, very low level API. They all run on Braket ultimately, but how would you advise a customer which environment to use to achieve the best results for them?
So our view of who are using these devices is constantly changing. We are learning more and more about what our customers are wanting. And really, what we learned is that customers such as qBraid and Strangeworks, who build on Amazon Braket, appreciate the level of possible integrations that AWS and that the Amazon Braket service offers as being an AWS service. So I would say that's the strongest reason to consider AWS. If you're building something on top of it, you want to rely on APIs not changing, you want to rely on operational excellence, 100% availability. All that is offered because the Braket team complies with the AWS mandates and requirements.
Good. And Kenny, how would you answer that question? I mean, we've seen some really cool stuff from you and also from James and Peter. How would you advise the customer where to start and why to start there?
I mean, yeah, obviously in my biased opinion, you should start with QBraid. But in reality, I think that the size of a customer as well as the kind of like quantum maturity of the customer is kind of going to dictate that quite a bit. While larger companies might have an entire IT team where they can, have all the AWS services set up for them and provisioned properly, I think maybe some smaller teams might find it more useful to go with people like Strangeworks, people like QBraid, etc.
And how about hybrid jobs? I guess that's a question to everyone. Some quantum algorithms use both classical resources as well as quantum resources. How well does the environment support hybrid jobs? James, maybe you want to go first?
Absolutely, yeah. So Strangeworks supports hybrid jobs with AWS and also Qiskit Runtime, which is their hybrid framework.
Wonderful. And Peter?
So Amazon Braket Hybrid Jobs is available not just through the API and the Braket SDK, but also in the notebooks. So it's all present in there and it works pretty well.
Great. Kenny?
Yeah, ditto exactly what James and Peter said. And then maybe one extra thing in addition to that is the qBraid runtime orchestration that we've developed also makes it really possible to kind of orchestrate HPC and quantum.
And one last question. We mentioned earlier in this webinar, Blockade. Blockade is the development environment that it's an open source environment that QuEra provides, and it allows you to simulate the job on a certain number of qubits before submitting on the real machine. What kind of simulators do you offer on, Peter, let's start with you, and then James and Kenny as we wrap up.
So the Python SDK comes with what we call local simulators. These are running on the local hardware of the deployed stack that the customer chooses to do. So that can simulate state vectors, density matrices, and AHS. And then we have managed simulators which run on AWS hardware, and they act as Amazon Braket devices, and those can simulate circuits as well as noisy circuits.
Good. James and Kenny?
Yeah, so we provide access to all of the same simulators through AWS. Once again, also through Azure. On the optimization side, we provide access to some kind of simulated annealing solvers as well as some hosted simulated solvers as well.
Same again, and then in addition a little bit, we do focus quite a bit recently on GPU accelerated simulators. So actually the QuEra compiler simulator infrastructure right now is being hosted on our in-house Grace Hopper NVIDIA server. And we also do that for a lot of other devices.
Wonderful. Well, thank you very much for demonstrating your excellent environments, and thank you for the participants in this webinar. A recording will be available soon. Join us for our upcoming webinars. You will receive messages. And thank you again for spending the last hour with us.